Again, yeah. Hey, everyone. I'm Matt Knight, as Loris just said, and I'm from Vancouver, Canada. Um, when I was a teenager, I tried to learn how microcontrollers worked. I was super fascinated with them. I was into like hardware, but there was like a disconnect. I could do. I was using Arduino, but there was this like high-level programming like layer that I was at, and then there was like all the hardware that I was able to understand, but there's like a massive missing gap. And it wasn't until university where I had like the right resources, mentors to kind of fill in those gaps. And to be honest, it was a little underwhelming. Um, like the teenager version of me could have totally picked them up, but there's some issues with, accessibility of like this information. So today I'm gonna go through. My main goal is if even you may not be into embedded systems, but I want to equip you with just the right amount of information to be able to break them down and understand them at a low level, so you can pursue your own projects. So there's a couple like activities and goals I like to do, or like in general when building an embedded system, and I'm gonna just like cover those quickly. I'm going to talk about like the status quo and how I had a lot of trouble learning how this stuff worked. I'm going to then hopefully that'll be kind of like from like my teenager to my university years. I'm hoping to shorten that from like several years to like, a few minutes for you guys. And then I'm going to break down those fundamentals that I learned. It's not that it will be underwhelming. I'm sorry. And then I'm going to talk about some of the work we're doing at the embedded group, Zig Embedded Group. So goals. One, collaboration is super important to me. I love, building stuff with my friends. And when I, have a repository of code that's supposed to run on hardware, I want someone else to be able to reproduce, build it, and have it run. That's usually kind of hard. I want to make sure that concepts within the code base are kind of like linked. So if someone's reading through it and they don't have me there to like point things out to them, they'll be able to kind of go through and find things. And then I want them to be able to modify that to their heart's content. The other thing is I want to be able to run on all sorts of hardware and to work with it. I want to be able to like fit the spec that I actually have instead of like throwing a massive machine at a small problem. I'd rather be able to tailor it a little bit better. This is useful for like any low power applications, space constraints, and it does come in handy because there is part obsolescence. Manufacturers only have parts that they'll only make parts for like 15 years. And if you're actually working on a product, you have to deal with hardware no longer being in existence. And then the other thing is like recently we had supply chain disruption. I know a website that literally was just like posting cute little videos of like, this is what else you can't get this week. And then it's also good for education to be able to, like play with different hardware that behaves slightly differently. Other thing I want to do is custom boards. They're super gratifying to make. They're super accessible these days too. You've got KiCad, which is like a full studio to create these things. It's backed by CERN, the particle accelerator, and it's at par with professional level software today. The other reason, like the reasons for doing this rather than just fun, is that mechanical and space constraints are pretty common. This here, by the way, this is not my board. This was made by some friends of mine in my graduating class. What they did was on the PCB, they were able to route traces for a coil. And what this does is that it's a rotational transformer that wirelessly transmits power and data. This was for a boat steering wheel. So you could like turn it infinitely and have like a bunch of lights and controls. And finally, I want to leverage my hardware. I want to squeeze everything I can get out of it, or I want to be able to give it some, like, have the same hardware and have the binary size not balloon too much so I can update it later. This is my friend Robert, and he's wearing what his group called the SMART hat with a D, and I'm just going to leave that. There's not going to be any more context around this. Okay, so the status quo. So I'm gonna kind of there's gonna be like interleaving threads of like, you know, things that are pretty straightforward, and then it's also gonna be mixed in with like a rant. So here we go. So let's start, you know, embedded systems. It's really hard to like pin them down. So I generally see is like if you're typing on a keyboard, looking at a screen, that's not an embedded system. If it's in a data center, no. Phones, like it's in the middle, but I don't really care at this point. What I like to think about is like you're dealing with usually like physical phenomena, and there's some like hard real-time constraint. A microwave is a great example because you've got, you know, your front dial pads, but then it has to control the, I think, dynamo for like, you know, zapping your Jiffy Pop. Also, I wanted to like quickly say we're not talking about any operating system right now. We're just doing bare metal development. Operating systems get like there's a lot of things we can build out of there, but I just kind of want to focus on dealing or interacting with hardware from our programs. So here's a microcontroller. They're usually kind of like everything in one package, all the kind of like computing resources you're interested in. So you've got like your volatile, non-volatile memory, you've got your CPU with all of its components, and then the good part, the meat and potatoes is the peripherals. Wait one sec, those are backwards. So peripherals, you've got general purpose input output pins, so you know, turning on LEDs, reading input from buttons. There's a ton of different digital communication protocols for like interacting with other devices. You've got interacting with analog circuitry, think, you know, speakers, motors, different anything you'd, you know, interact with a control system, and more. And the thing is, like, there's a lot of architectures or CPU architectures in embedded. Before ARM really like took over the market, a lot of companies would just like make their own architecture for very specific applications that have their own like C compiler. They might promise a C++ compiler, but they wouldn't, like, they're a hardware company, not a software company, and they wouldn't really finish a lot of the features required. You're dealing with like 8, 16, 32-bit. You're also dealing with Harvard and von Neumann architectures, so the data and the instructions might be on different memory buses. So there's a lot of variety, and it's fun interacting or working with all these. Here's a search page on a company called DigiKey. They're a massive electronics supplier, and it's kind of busy, but what's happening is I've just selected, I want to know about all the active microcontrollers that you're able to sell me. And you can see we've got almost 50,000 options to choose from. Now, there are some duplications in that list. So what you'll find is like for different temperature ranges or different physical packages like this, you can have the same like core microcontroller. So, but we're still dealing with like hundreds to thousands of like normalized microcontrollers to think about. And then, okay, so we've you know, picked our hardware that we're interested in. Now we want to program it, right? Everything on the left, every single bulletin point is like a full-fledged IDE made by a manufacturer. I put the manufacturer name in some of the points. You'll notice one manufacturer may have like multiple IDEs. And like the reason why there are so many makes sense, but as like a beginner or a hobbyist, you walk into this and you're like, I don't know what I'm doing. I wanted two special notes: Espressif, ESP32, if you guys haven't heard of it, and Nordic is another. It's a Bluetooth-based company. They were kind of nice. They don't make an IDE. They make a tool chain. You can incorporate it to VS Code or whatever you want. But yeah, for the most part, it's really difficult trying to download one of these IDEs and figure out what the hell's going on. And ultimately, like, what they hide from you is like, I didn't even know what makefiles were until after university, actually. There's also things called linker scripts for taking your object code and mapping it into exactly where you need it in memory. Different microcontrollers are going to have different blocks of memory in different locations. It's not really clear what a compiler is when you work with these tools. Interrupts are some sort of black magic. I'll talk about interrupts later. And then getting your code onto the microcontroller is just a play button, which is a problem because if you need to understand how to do any sort of firmware upgrades in the field for your product, or you're just interested, it's very difficult to kind of like separate that from the tool itself. Yeah. So let's deal with the fundamentals. These are the things that, like, after a long time, I was able to figure them out, and it's kind of nice and straightforward. So we're going back to our microcontroller here. We don't actually know like how this guy works. Let's assume for now we can get our program into Flash. We can execute it. It's great. But the way we interact with the outside world is through the peripherals, and we have no idea how that works yet. So the main way is called memory mapped input-output or special function registers. Pretty much what you have is you'll have your address space, and there will be like very specific addresses where if you toggle the bits if you just toggle the bits, you'll be able to interact with the hardware. So what this might look like is this is from the ATmega 328P, which is found in the classic Arduino. At address, hex address like 25 is the data register. If you want to turn an LED on like a certain pin, you just write a 1 to that bit field at that address, and you'll be able to interact with the hardware. So, for example, and I guess the contract and how you deal with the hardware, it's completely implementation based. So you do need to read the data sheet. And this is a pretty straightforward example, but then you get into stuff like transmitting over a serial line, like just classic stream of bytes. So here's like a zig function. What we're doing is we're taking a payload, just a number of bytes, and we're going to send them over a line. And so what we do is like we go through the payload, we wait until the UART is writable, and then we assign a byte to a specific location, and then we loop back around, and then we wait again. This, though, you can imagine, if this is a slow protocol, we're essentially spinning a lot of the time. And especially for like UARTs, we could be talking about like thousands of bits per second. So you're just wasting a ridiculous amount of cycles if you needed to do something else. The next one is hardware interrupts. So pretty much every microcontroller will have kind of like a specific static table going from an event to a callback, pretty much. You can set this up at compile time. Depending on your hardware, you might be able to also do this at runtime. And so what happens is, let's say we've got our program here. So this is a program memory. We'll have our interrupt table. It's already configured for us. We'll have our ISR interrupt service routine, which is our callback, and we've got our main program. So we'll just be like executing, and what the interrupt does is that it'll fire. So for example, this could be a button being pressed. This could be an analog to digital converter, which is reading from a microphone. And stuff like audio, you need to be sampling at constant periods, and it has to have very little jitter in order for the signal to be understandable. So we've got an interrupt that's been triggered. The CPU is going to look up the corresponding handler for that event, and then it'll jump over to the interrupt service routine, execute it, and then continue back from where we were. There's some other information about like how the stack is used, but that's usually those details we get closer into like hardware specific features. And so transmitting with an interrupt, instead of busy looping on that is writable, what we can do instead is we can kind of like set up our table. We set up a buffer we want to send to, other end of the line. We turn on the interrupt. We just enable the interrupt, and then we can go do other things, which is nice. And then what will happen is the interrupt will fire, and as we're doing our other job, it'll just jump to the other interrupt service routine and then send out all the bytes. And then you can build on top of that. There's real-time operating systems and a lot of other fun stuff like that. But like for dealing with the hardware, like that's about it. This is the stuff where like I learned about MMIO, interrupt service routines, and then I was like, okay, but what else is there to interact with the hardware? But like just knowing that like, okay, like that's about it. You can go through you will not be dealing with the registers, raw registers like that usually. But what you'll find, you'll deal with different like APIs, different drivers, high level or like things that are abstracted for you. But it's good to know how this stuff works because sometimes the hardware has a certain ability, but then the drivers or whatever libraries are given don't actually give that ability to you. So you can hack it, you can make it work for you. So now I just want to talk about the Zig embedded group. So a few, Zig itself, when I first saw it, I thought it was really attractive for embedded development. I didn't get into the pain of tool chains at all, but the fact that we can have like one binary and just like do Zig build and have it compile, that's it, is super powerful. It's got extensible like a build system. So I mentioned like everything we've wanted to do in the Zig embedded group to like encapsulate the build information. We haven't had to do any hacky shit pretty much. Which has been awesome. And then the language itself, number one, I really like languages I can fit in my head. The really cool part is with Zig, I'm not sure how much you guys have gone over it or know about it yet, but one of the conventions it uses in the standard library is that you give it an allocator handle in order to allocate dynamic memory. When you do that with embedded systems, you actually allow for the standard library to be used on a microcontroller very easily, where with C or a lot of other languages, what you'll find is like you need to have malloc implemented, so you need to like allocate part of your memory as a heap, and a lot of like buffering goes on behind the scenes. The explicit error handling is great, and then comp time is just endlessly useful. So we made kind of like a library, microzig. It's a few things in one, so it makes it easier to target specific microcontrollers. Besides like ARM, there's a bunch of like specific cores with different extensions to their instructions. There's different startup code you're going to need. We have a cool thing with interrupts I'll get to show you in a second. And it's very unstable right now. Right now, Zig is going through a lot of changes. In the next few months, we're planning on kind of like spending more time making it stable across different versions, but we've been just running with Nightly for the last while. So this is code for, as part of the build system. So you can set up a specific chip. There's a generated code that we have, and then you can set up your memory regions, and then you can just pass this into this like add embedded executable, and this will just compile your program for you. For MMIO, so I don't know if anyone's done a bunch of bit math before. It's really easy to like fuck it up. So one of the things we have is we're able to leverage some of Zig's comp time capabilities and language features to have really low overhead abstractions. So they fit really nicely. So we have this modify function. And so what it'll do is that like for the first one here, it'll set UART, EN, and the other two flags to 1. Modify will read that register, apply these changes to those fields, and then write it back. And that's nice because I know I'm going to be doing read, modify, write for each one of those, and there's no extra overhead there. For interrupts, we have this is one of my favorite things is generally in C for interrupts, it's all like compiler magic. So you'll have a like pragma ISR, and you have to know a specific string in order to get your interrupt handler into the right location. And then if you get it wrong or you have the wrong chip, it doesn't really give you that much information. So here we just have like a interrupts namespace, and then we just name all of the functions that matches up to the table that the microcontroller has. And the thing is, if you get it wrong, boom, what we do is we just list out, like, Blarg is not one of the handlers that you're allowed to install. Here's a list of all of them. And then also, even when we make relatively high-level code, it does generate very small output, which makes me extremely happy. It's like we're in memory-constrained devices, so it's meeting that goal I have of like being able to squeeze out all the performance I can. So for a while it was experimental. We were like, this seems like it would be good, but what we're going to do is we want to actually like show people. So Loris ran a conference called Software You Can Love in October, and he was gracious enough to give me and my friend Felix, he's the happy-looking guy in they're both looking happy. The guy on the right in the center photo. So him and I ran a little workshop with, I think we had like 6 people there. And the thing that made me joyous was the fact we spent 0 downtime on anyone's dev machines. They were able to just do zig build as a command, everything compiled, and it was great. So now that was like evidence that, okay, maybe what we're doing and what we're building is good. Let's continue to do so. So actually, I'm running a conference in Vancouver this June. If you're in town, there's going to be another embedded workshop. This time though, I'm going to add maybe a little synth portion. I'm pretty excited for. But yeah, and that's all. Thanks for letting me share my stuff.
Okay, before we move to questions, Matt, I think you forgot to mention probably the most important type of embedded device, mechanical keyboards.
Oh my God.
Who here is into mechanical keyboards? Yeah. We eventually plan to write our own Zig-based firmware for keyboards because QMK, ZMK, not bad, but yeah, the tool chain, it sucks. Yep, so Zig build, boom, firmware on the keyboard. Okay. Questions now. Anybody? Oh, I see one.
Thank you.
Hi, thank you for that. I'm going to be honest, 90% of it went over my head.
Oh shit! Oh,
Where
supposed to do that.
where can I learn more?
Where can you learn more? I would say I would start with hardware. Specifically, I would go MicroPython with Raspberry Pi's new microcontroller, the Pi Pico. That's got a lot of it's a lot easier to get started with that stuff, and you'll be able to when you're programming this stuff, there's so much friction a lot of the time. You're naturally you just don't have the same debuggability, and you want to make sure you're motivated and you have fun. So I would say MicroPython and that hardware.
Great. That actually helps because I've got a Raspberry Pi that's collecting dust at home. So
Oh, nice.
yeah, thanks.
Any more questions?
Yeah. Since we brought up MicroPython, then why, at what point do I want to start using Zig?
Couple years, probably.
Or under what, what is the train that leads me towards Zig from something high level like MicroPython?
Probably maturity in some of the support libraries. One of the things I'm working on specifically is building tools, because you've got to build out and kind of do a lot of repeated work if you're going to cover a lot of hardware. And so the stuff I'm working on primarily is making tools to reduce the amount of work that takes, so that we can reach more hardware. And also like educational materials, like that's something I'm really wanting to do, is like have a nice embedded book that breaks things down, and have a bunch of example projects you can do yourself.
Matt, but maybe you could describe what you give people when they attend the embedded workshop that you run.
Okay, so you get your own little hardware kit with a breadboard and small components. One of the big things I was really happy about was we were getting software engineers to like breadboard and wire up their own circuits, which is a lot of fun. And so you'll have a bunch of examples taking you through like using those different peripherals, and then hopefully we'll get into some of the hardware interrupts I mentioned, and then you can take that kit home with you and experiment to your heart's content.
Thanks, Matt, for awesome talk. I wanted to ask, what is the least amount of memory that you've worked with? And have you ever exploded a board?
I have exploded a board, yes. I think it was a motor controller. They're so easy I think I just wired something wrong, and you're dealing with stuff that can output a lot of current. Yeah, it scared me. For the lowest, so I think the funny part was, okay, another thing I'm gonna complain about. So our school IDE, we used Texas Instruments stuff primarily at my school, and we had the lowest amount of like memory for program I could use was 16 kilobytes. Even though the board the chip had 190 something, it was because it was the free version of the compiler, so they limited how big your programs could be. Yeah, I love that shit. Well, Zig I could. Yeah, I actually just wouldn't use their compiler because it was kind of annoying to deal with. Now I'm actually, one of my things is like I bought one of the old boards from school, and I'm going to like get my stuff running on it and then feel good about myself.
Any more questions? No, I think we're good.
Sweet.
No. So please give it up for Matt.